wonder if AI can spot a magic trick. Imagine a ball rolling behind a wall and it never comes out the other side. Weird, right? Or think about pulling a block from a stack of building blocks. The whole tower falls. But what if it just floats there? Our brains know that's not how physics works, but can AI figure that out too? Today, we're diving into a model called JEPA that's learning physics just by watching videos. Instead of looking at pixels, it predicts what should happen next using its own learned concepts. Kind of like how we imagine what's behind that wall or what happens when you pull that block. It gets it right most of the time, even without rules coded in, but it still gets stumped when objects interact in tricky ways. So, how does it work? Why does it struggle with some stuff? Let's dive in.
Let's begin by talking about how humans, and even many animals, seem to know basic physics almost from day one. We know instinctively that objects don't just vanish into thin air or pass through solid walls. Babies stare longer when a ball disappears, and birds carefully test the stability of a branch before landing. Researchers refer to these innate abilities as core knowledge. It's like we're born with certain systems that instantly sense when something in our environment breaks the usual physical rules. Now, there's a funny paradox in AI, sometimes called Moravec's paradox, where things that are effortless for us, like judging if a ball can roll behind a wall, can be extremely difficult for AI. Meanwhile, AI can be fantastic at tasks like math or language. Why is it so hard to give machines the kind of common-sense physics we don't even have to think about? Historically, there were two main AI approaches for this. One used structured models with hand-coded rules and simulation engines. Think of it like giving the AI a tiny physics sandbox. The other used pixel-based methods, which simply try to predict future frames in a video at the pixel level, hoping to learn patterns directly from raw data. Both methods have drawbacks. Structured models need a ton of manual rule encoding, and pixel-based models often stumble when the scenes get complicated. This paper introduces a new middle ground. It aims to learn physics by predicting video outcomes in an abstract representational space. So instead of juggling raw pixel details, the model focuses on patterns and object interactions at a higher level. The truly interesting part? This approach picks up on basic physics in just about a week of self-supervised training on videos. That suggests I might not need rigid, hand-coded physics rules if it can learn from observing the world, much like humans do. Let's dive deeper into how this model, called Video Joint Embedding Predictive Architecture, JEPA, pulls it off. It's not like older structured models with explicit rules, and it's not stuck predicting every single pixel either. Instead, it operates in a learned, abstract space. The idea is straightforward. Feed JEPA natural videos and make it predict parts of the frames that were hidden or corrupted. By comparing these predictions with the real video, the model figures out how wrong its guesses were, what we might call a surprise signal. Then it extends this approach to future frames. So if everything unfolds normally in a video, JEPA's surprise remains low. But the moment it sees something that violates physical laws, like a ball poofing out of existence, its prediction error spikes. Check out the graph here to see how sharply that spike appears and then gradually settles back down. In tests, JEPA shows impressive results. On a dataset called INTPHYS, short for intuitive physics, which checks if a model can spot impossible events, JEPA scores 98% with zero special tuning. On another dataset, INF Level Lab, it gets 62%. Compared to both pixel-based methods and large language models, it's closer to the way humans perceive physical plausibility. Pretty neat, right? Now, how does JEPA measure what we'd call intuitive physics? It uses an idea from developmental psychology called the violation of expectation paradigm. You know how a baby stares longer at weird events, like a disappearing ball? That longer stare is a sign of surprise. Here, we want JEPA to do something similar. The model watches videos where one is physically plausible, while another breaks some rule. It forms an internal representation of what's supposed to happen next. Then it sees the actual outcome. If reality matches its predictions, surprise stays low. If not, the difference in the model's internal representations spikes. That's basically the AI version of a baby's confused stare. Crucially, JEPA doesn't bother with raw pixels. It encodes each frame into a condensed representation. Then a predictor module guesses what the next encoded frame should look like. This way, the model focuses on high-level patterns, such as objects persisting over time, rather than getting lost in the noise of small color or texture changes. And by varying how many past frames are given, the researchers can test whether the model remembers short sequences or longer arcs. The result? A system that detects physical nonsense on its own. No extra labels or training required. Here, the paper shifts to how VJEPA is evaluated across 3 datasets: EHESS, GRASP, and INF level lab. Each dataset tests a slightly different set of physical principles, from whether objects remain solid to whether they move realistically. This variety helps ensure the model's not just memorizing a single type of trick. The researchers also line VJEPA up against other methods to compare performance. One is Video MAEV2, which tries to predict future frames at the pixel level. That means its surprise measure also comes from a mismatch between predicted and actual frames, but it operates on raw images rather than abstract representations. Then there are large language and vision models like QN2 VL7B and Gemini 1.5 Pro. While they can generate visual or textual predictions, they aren't primarily built for video-based physics tasks. How do the results look? VJEPA hits about 98% on EHESS, 66% on GRASP, and 62% on INF level lab. Not bad for something that wasn't specially tuned for any of these tasks. Video MAEV2 does okay, but it still trails behind, and the big language and vision models lag even more. If you look at the comparison tables in this section, you'll see how VJEPA holds an edge in spotting impossible events, all thanks to that representation-based approach. Next, let's talk about the specific physics concepts VJEPA manages to capture. Check out the bar chart here, which breaks down various categories: object permanence, shape constancy, continuity, gravity, and so on. You'll see that VJEPA far surpasses random networks in understanding these principles. It does especially well with object permanence and shape constancy, recognizing that objects keep existing even when out of view, and that they keep their shape over time. In other areas like support, do objects hang in mid-air or fall? VJEPA also shows strong gains. However, for solidity, can objects pass through each other? And collision events, the improvements aren't as significant. The scatter plots comparing VJEPA's error rates to human performance are especially interesting. Look at the left plot for relative error and the right one for absolute error. In both, VJEPA hovers around or below the diagonal line, suggesting it often matches or beats human predictions in these synthetic setups. Statistical tests confirm that VJEPA's advantages are usually significant, except for collision and solidity, where it doesn't outperform simpler baselines. On real-world scenes, like in INF level lab, VJEPA's strongest suit remains object permanence. Essentially, it's learned many of the same rules we humans intuitively know, though it still has some blind spots when objects interact in more intricate ways. Now, let's look at what design choices make VJEPA so effective. One big factor is the masking strategy. Picture covering a chunk of a video with a block and asking the model to fill in that missing information. Using square block masks teaches the model to pay attention to larger, more coherent regions, perfect for understanding that an object continues behind an occlusion. Adding a causal element, where only future frames are masked out, helps a bit too, because it forces the model to predict how the video will evolve. But random pixel masking is less beneficial, since that scatters missing bits in a way that doesn't align well with real-world occlusions. Another key factor is the dataset. Training on How to 100 Million, a huge collection of instructional videos, gives the best results. Even a subset as small as 128 hours from this dataset yields solid physics understanding. Other video sources like SSV2, which focuses on human motions, or K7 10 inches, various activities, work decently, but not as well as How to 100 Million. The takeaway? Seeing a wide range of activities and object interactions helps the model learn more robust physics. Finally, model size is also relevant. As you increase VJEPA's parameters, its performance gets better, though the jump from medium to very large isn't huge. The smallest version still does considerably well, indicating you don't necessarily need an enormous network to learn intuitive physics, just a well-structured approach and solid training data. Here, the paper recaps the 3 core ingredients that seem most crucial for building intuitive physics into VJEPA: the pre-training task, the data, and the model size. First, the pre-training task. It uses what we've been calling block masking, where a block of video is removed and the model has to reconstruct it. Interestingly, simply reconstructing hidden portions can be more effective than explicitly predicting future frames for learning physics. This is a bit surprising, since many video tasks focus heavily on forecasting what comes next. But for physics, it appears that filling in missing regions provides enough clues about object continuity and interactions. Second, we have the training data, Saloni. SSV2 mostly has human actions, so it's a bit limited in scope. K7 10 inches is broader, but still not enough. How to 100 million inches stands out because it includes a massive variety of scenes, objects, and actions. Even just 1% of that dataset is enough to get JEPA above 70% accuracy on physics tasks, demonstrating that diverse, high-quality data is worth more than sheer quantity. Lastly, model size. It's true that bigger models generally perform better, but you'll see in the table that even a modest-sized JEPA passes the 85% mark. This suggests there's a sweet spot. You don't need an enormous system if your training strategy and data are solid. Let's wrap up with a summary of what the paper accomplishes and where it still falls short. The main message is that a robust sense of intuitive physics can emerge simply from self-supervised learning on videos. JEPA manages to encode core ideas like object permanence and shape constancy without being explicitly told to do so. Instead of pixel-level predictions or hardwired rules, it builds a mental model in an abstract representation space and uses surprise signals to detect violations. That said, there are limitations. JEPA still struggles with more complex interactions, like when two objects collide, or when stability and balance matter. Part of this might be due to the relatively short timescale it considers, or the lack of certain event types in the training data. Plus, the model is only passively observing. It doesn't attempt to see how its own actions might change the outcomes. Looking forward, the authors suggest training on even richer, more infant-like videos to capture how children learn over time. Future versions could also incorporate advanced ways of modeling object interactions, bridging the gap between simply spotting when something's wrong and actually predicting how collisions and complex dynamics unfold. Despite these gaps, it's clear that this approach, learning to fill in missing video segments in a way that focuses on higher-level representations, is a strong step toward building AI that grasps the physical world in ways that feel more like our own intuitive understandings. Thanks for joining us today. Happy learning and stretching together.